we're going to get going. We are excited about this. So this robotics presentation, as you can see, is one that we put a lot of work into, and we're proud of where it's ended up. But these things really don't quite work unless you have a pretty nice team. One of those team members, of course, is NIRO. It's his birthday today, his second birthday. So happy birthday to NIRO. Worked out very well. But beyond just NIRO, you'll have me. I'm Sagar. This is Kim over here. Kim and I are going to do the presentation. But as you can see, there's a lot of work behind the scenes that has to happen for robotics to work properly. And so John and Fabian are going to be manning the robot. John personally, Fabian over a remote desktop. Nico's helping us over here. We've also had Clara as a huge part of our project, but really we can't even begin this presentation without properly thanking Petar Kormushev, whose Robot Intelligence Lab and actual robot we used and we exploited as much as we could. And of course Andy Davison, our Department of Computing Supervisor, who kept us going the whole way through. So thank you all very, very much. The thing is, once we realized that a lab like Petar's existed here in Imperial, we got very excited. We like the idea of doing something hardware focused. And the reality is that most robots today look something like this. They're fixed, they're stationary, and they're often industrial. But when we think about robots, when we get excited about robots, we usually think about someone like this, in case any of you recognize it. A domestic robot, right? A personal one, someone that you can interact with, ask questions. And actually, we had a particular heuristic that worked really, really well for us. So imagine that you are, say, someone who's disabled or not able to walk for some reason. And in your home, in some slight soon-to-be future environment, you had a robot that could help you out. You could ask that robot, would you please go fetch me a particular bottle of medicine from the kitchen and bring it back to me? So we used this as a really useful tool to help us realize what we needed to include and what we didn't need to include. And so we'll be coming back to this over and over. But to be honest, our demo is this. It's a fetch demo. This turns out to be a really critical building block of many more complicated robot features. And we think that the best way of showing this to you is just to do that, just to show it to you. Let NIRO rock and roll the way that he wants to. So things can sometimes be a little bit iffy, but we're going to go ahead and try a demo through. If you will bear with me, we're going to do some audio in. So please, if you can, see if we can keep the noise down. We have a little bit of ambient noise, but hopefully it'll work. John's going to set some of this stuff up. What he's going to do first is set up the map that NIRO's going to move in. NIRO has mapped this space. We came here last Friday and made sure we got exactly this space. And then he'll tell us when he's ready to go. What John is doing is he's verifying that the wheels are ready to receive current. After he does the full demo, we'll go through in detail and break down all the components that came in.
Ready to rock and roll. Ready for your command.
Hey NIRO, fetch me a coffee.
Command received. I heard. Coffee. Just taking a picture. Smile please. Thanks, John. I am navigating through the room. I am searching for the coffee. I managed to pick up the object. I am returning to where I started.
Okay, let's see what NIRO does now.
Trying to find John.
I'm John.
Hey, you're not John. Get out of the way.
Hey buddy, did you give me the coffee?
I see you, John. Here's your coffee.
Thanks. Hey guys, round of applause for robots. Right off of our shoulders, let me tell you, it can be tricky to work with robotics. And I think that one of the reasons that we were all careful about this presentation, wanted to make sure it goes well, is because NIRO has a lot of parts. And we came to realize that robotics is this fundamentally multidisciplinary activity. You have to take all these separate pieces of hardware and get them to synchronize together. You might see names you recognize here. This is just a Microsoft Kinect from a video game system. Yeah? Some of these are just off the shelf. This wheelchair base we got off of eBay. There's of course more complex components like the arms, the LiDAR system, but to get these things to interact is not trivial, right? They have their own SDKs, their own languages sometimes that they operate in, and we had to contend with this problem. If we had to do everything entirely from scratch, we would have to spend this project working on networking, concurrency, all of these types of issues. But we were helped. We were helped by having something called Robot Operating System. Now, ROS is neither an operating system nor a programming language. It's something in between. It's a type of middleware. What ROS is it allows you to set up, given a particular file structure in Ubuntu, it allows you to set up a series of graph-based nodes, right? So these different components sort of exist independently. They live even in their own language, although we tended to code everything in Python. And then they allow communication across the network. So ROS essentially exists the ROS master exists as a registration table, and it does lookups and sends people along. So that's what's happening in the back end for ROS, but it's particularly useful when it comes to communications techniques. We use two core types here. We use publishers and subscribers, and on the other side we use services, which work with clients and servers. Now, on the publishers and subscribers method is actually pretty typical for a graph-based network. In this situation, basically any node on the graph can broadcast, and anyone can choose to listen to that signal. The server process, the service process, is a little bit more like a function, right? So you send in parameters, something like, say, the ARM does processing and then returns you back a return value. So that's how this works here. The way we instantiated this was actually we created parent classes for both types of communicative processes, and then we created child objects anytime we needed to do that through. So that backend was a really useful tool for us to keep things all linked up together. But that almost offers you too much, right? Because you're taking in video, you're taking in navigation data, all sorts of different types of communications. We needed to simplify things a little bit, right? We wanted to make things just a little bit more modular, a little bit more precise. For this, we decided to use a state machine. So I'm sure many of the more experienced computer scientists know all about how state machines work. For us, this was pretty exciting and a really useful tool. Basically, it means that the robot exists in one of a series of finite states. When in one of those states, it just does usually an atomic action, one core thing. Not always this way, but most of the way it is. When you saw NIRO go like this with his arms, where he kind of woke up, that was him initializing. And in that first state, we have him go through a gauntlet of tests, a bunch of checks to make sure that things work properly. And then he comes into idle, which is actually where he was just now. Well, that's why you heard him again, because he goes through this whole cycle. So for the rest of this presentation, we're going to mostly go through these major chunks of states and explain the major component that's going on here. And hopefully that helps you understand how we linked everything together. The very first one, a straightforward one, is to do command inputs. Now, look, we go back to this idea of someone who is unable to walk and who needs to make a command. The most straightforward and reasonable way to do that is through audio, to say the command. But we're really just trying to get to this object. We just want to know what you're getting. We could get that command in other ways too. We've used, for example, these types of object signs in the past to directly tell the robot through sight, this is what we want. You could even type it on the command line. Lots of things you could do here. Audio was tricky for us. We first started using an Amazon Alexa device. We had to use an AWS backend, but requiring an internet connection at all times makes things sometimes a little bit unstable. And we really wanted to do something offline. So this solution uses an offline solution for a more limited vocabulary. It uses something called CMU Sphinx. And even though it's a pretty simple grammar structure, it was the best when we optimized. We tried more complex ones, simpler ones. This really worked quite well for us. But that's really important, right? Because if someone gives you a command, let's say you're a carer, right? And you've been given a command, you need to both understand it, but you also need to know who's given that command to you. So if you tell me that I need to go get a bottle of medicine for you, then I'll head off and I'll get something, but I can't come and deliver it to someone on this side of the room. I need to know you, right? I need to bring it right back to you. So a pretty straightforward way of doing this would be of implementing some sort of facial recognition. We use a machine learning technique for this. It was based off of a ResNet CNN model. And what happens here is we have a few saved faces, but it just so happens to be our faces. And we have a pre-trained model. And all that happens is anytime a new frame comes in through this Connect camera, we go through the process and output a vector encoding once we get through the CNN, and we do the same thing for the saved faces, and we simply compare the two and see if they're really quite close. If they are, we have a match. If they aren't, then either we don't have a match, or maybe we don't even have someone there at all. And so that's what we use. It's actually quite robust. The reason we're showing you such a deliberately poor picture with bad lighting, poor facial angles, and with multiple people is to show you that it works even under these types of conditions. So it really works quite well. When it was seeing John, it could also see us in the background, but still recognize that John was the one right there. So to do all of this, you probably noticed that NIRO speaks to you. That audio output is a really simple thing, right? It adds personality, it adds some fun, But we found that this seems pretty common around robotics, and you folks can correct me, but it seems that a lot of the features that add personality often are really useful for debugging too. So we know exactly what state NIRO is in when he says, I'm idling, right? And then we move on to the next one. So this becomes a really useful tool for us, particularly for more complex situations, like when we're doing mapping. So you'll recognize this room. This is exactly where you are. And we had to keep these seats clear because we needed some static objects here. The markers are sitting, I think, right where we put them, right? Oh no, maybe not quite. To do this, we use this machine down here. This is a LiDAR. It's got shin height, and it sends little pings everywhere. When it gets a returned back response, it knows there's an object there. And so before we did this mapping, we cleared the space of any dynamic obstacles. And that way, when NIRO is moving inside of this map, anything new it sees has to be dynamic. Very often it's like someone's leg, right? But it could be something else new that shows up. So to set this whole thing up, NIRO adds a little layer, a little buffer of blue everywhere. And that's for safety reasons, so he doesn't get too close to any particular object. He's a little imprecise, as you saw, with some of his movements, and that can lead to problems if you're not careful with this sort of thing. To actually do the navigation, though, is tricky. We tried a whole bunch of different packages. We had a lot of trouble, to be perfectly honest. And the one that we really like creates a path. It's a bit tricky to see this, but you might be able to see this green line here. That's NIRO making a path to his goal. When he does that, there's a series of velocities that he decides on for each of those paths. And now in this particular example, you're seeing something come into that space. In this case, it was actually a human that walked in space. And you can see how NIRO has altered his path to deal with the new obstacle. If he has enough time in space, he'll do that. So there's some really cool things he can do here. I mean, having arrived at this final spot, his job isn't done. It's far from done, in fact. So Kim's going to take over and cover the other parts of what's going on.
Yes, thank you. Okay, so once he arrives, the next stage that he goes into is the one that we call grasping. Grasping is really made up of two key components. One's called object recognition, the other is physically moving the arm from A to B. So let's focus on the first one, object recognition. So object recognition is a bit different from face recognition. Essentially, you need to be able to recognize the object, but you also need to be able to get the coordinates back, and very precisely where it is in space, in 3D. So we tried a lot of things here. We really spent a lot of time on this thing. But we very quickly, very early on, realized that there are three things that are super important here. Well, it has to be accurate, right? Like if we go back to the example of the personal assistant, we cannot pick up the wrong bottle of medicine. It also has to be robust. What we mean by robust is the thing that we didn't really, before we went into robotics, understand that there's a lot of uncertainties, right? The light might change, the angle is slightly off, all these things. We want something that is robust enough to deal with this. The last thing it also has to be is that it has to be flexible. We need to be able to extend it, right? So if there's a new bottle of medicine, just a new object that we want to be able to recognize, we want to very easily just be able to add that object, and you should be able to recognize it as well. We ended up going with the markers here, and I'll tell you why. So we tried a lot of things. We tried to train our own model with hard cascades. So that's a machine learning technique. That didn't really work so well. We also tried S detection, again, not very accurate. We tried a very advanced package that we downloaded, could never become stable. So when with these, they're very accurate, very robust, and they're very flexible. We can just print them out, and it would work as well with 100 objects as he does with 3. So there's a reason why these are very widely used. Okay, so now he knows where the object is. Now we need to get the actual coordinates. The way we get that is that we know exactly how large these are. Right, so I've removed them now, but we know exactly how large these are. So when we see it in the image view, we can actually infer how far away it is and infer the X, Y, and Z coordinates. Okay. So once we have that, so we have the right object and we know exactly where it is, we can go into grasping. But the coordinates that we got are relative to connect. Right? It's relative to this thing. Everything that the NIRO does, all this arm movement and so on, is relative to a space which is down here. So we have to first transform it. So we have to invert 2 axes and basically just use measuring tape and a lot of trial and error, which is really a common theme here in robotics. But once he has those coordinates, now we can finally reach for the object. So reaching for the object is a process of inverse kinematics. Essentially, the NIRO has 7 joints in his arm, right? So there's 7 angles he has to figure out. So you use an inverse kinematics solver for this. We did this, and we thought this would solve everything, and it would just be smooth, right? But we found that it actually just gives you a path from A to B. It doesn't promise you it to be an elegant one. So very often he would try to flip over the table, knock stuff over as he was trying to grasp it. Because he doesn't know there's a table. He just knows that there is an object that he's aiming for. So we wanted to solve this very pragmatically, and you probably didn't even notice, but he actually stops 15 centimeters in front of the object. You can change this. And then from here, he just has to go straight. This is to simulate that it's, for example, a shelf, right? So he can do funny stuff here, give him a bit of freedom, and then all he has to do is go straight. Okay. So now he's actually in front of the object with his hand. It's right on display, and now we want to grasp it. Yes, before we go into the next hero mode here, how does he know when to use left or right hand? In the beginning, he could only use right. We've also allowed him to use left, so we'll just measure if it's like on the left side or right side. That makes sense. Also, if there's a person who actually moves the object as he's reaching for it, sort of teasing him, he will realize that he didn't pick it up and he will try again. So we call this dynamic grasping. We have a video of this and we can pull it off if we have time in the Q&A session. But he's able to do this. Once he has the object, he goes into hero mode. I think you saw that when he comes up here, which we think is just awesome. Like, it's a bit of fun, right? It looks pretty cool, but it also has a very practical use. Because when he goes back, he will only come down, like if and only if he sees the right person in front of him. So there could be any person in front trying to say, I'm John, but he won't come down until he sees the right person, then he will lower his arm. So we found that to be super useful to actually understand if he has seen the right person or not. Once he's down, he has to hand it over. In the beginning, we have to just pull it out of his arms. But he's pretty strong. So what we do there is we're actually measuring if there's any force going onto his arm. If he just moves, so that could be a kid trying to pull it out of his hands, and he will open. So this actually works super smoothly. Okay, so you've seen what we've done with the NIRO and what he is capable of doing now. So I think one of the final questions to answer is, or the obvious question is this. So is there going to be a mini NIRO in all your homes by 1 year? So we think well, not quite. And so I think as a team, we're very proud of what we've achieved here. So it's been a very cool experience. It's been very fun working with this robot. And I think we've pushed the components quite far. We've also put a lot of effort into like making it elegant and like so it can be extended and play around with it. But robotics is tough. We spent a lot of time trying to overcome loss. It was not easy. There's a lot of uncertainties that we didn't foresee, at least. And all of these has to be tackled. And if we were thinking, if we had one more summer to spend on this project, just to give an advice for future students, we would probably work on these 3 things here. So for state machine, you maybe remember our state machine was pretty linear. There's a reason that we tried different things. But you could see a project potentially want to build something more advanced. Like, have some more advanced logic here, if then this, right, for each situation and state of the world. So that's definitely something you can play with. We've encapsulated everything in states, so it should be sort of easy to build new configurations. Next is object recognition. So we use markers, and there's a reason for that. And we think it will probably be a trade-off if you want to implement something new. But you could see that there will be a team that maybe try to build something that is really accurate, also robust, and flexible, but doesn't use markers. But it will probably be a trade-off. And finally, complete awareness. What we mean by this is that right now when the NIRO is moving around, he's only using his lidar at that particular moment. So he could bump his head into things, right? And there's a lot of cases of this where he's only using one sensor. And you could see it would probably be a very difficult project, but a project that could sort of turn on all the sensors. Like he has a lot. And then actually try to interpret all of this data, which would be difficult, but I think it would be very, very exciting if it works. Okay. So as a final thing here, because we're also thinking, how do we best hand this over to a new group? Because we found in the beginning, one of the things that really slowed us down was simply just the online community for robotics is not that advanced. It's fairly new, so there is some, of course. But compared to Python, if you have a problem, you can type it in and you get a response. We were hoping for the same thing, but we never really found that online. So we want to build a very, very good documentation. And we just briefly want to show you what we've done here, and hopefully this can encourage other groups to do the same. So we basically build a web interface. So it has everything, I think. So how you download, how you set it up, how you run, code snippets, alternatives, pros and cons, what didn't work and what could probably be extended, and so on. Like all of this is up there. And the reason for showing this is just we hopefully can encourage other groups to take on the NIRO, because we do think it could be an extremely exciting task, especially when it works. And we just want to end up showing you something that we thought was super cool. We got to participate in the Imperial Festival, which we found to be a huge privilege. And we want to end up showing you a picture that we're not the only one that could be quite amazed at what the NIRO is actually capable of. Look at these kids. Yeah? That is a pretty good picture. So with those words, I think we want to end here. So we want to open up for questions. I think we'll start with the markers and the faculty, and then we'll open up to the entire class. So feel free to ask any questions. But I think that's it for us. So thank you a lot for being here. Thank you.
We've got some questions.
Yeah, so what are some of the challenges in different kinds of objects that you could be asked to pick up, maybe in sort of environments? I mean, I noticed all your objects are nice and cylindrical. So, what other types of objects do you expect to encounter?
Yeah, there's this classic problem in robotics, which is, can you have your robot pick up a cat or like some other soft, wiggly thing, right? It's very, very difficult. I think you're completely right. These guys can talk about the ideal type of object, and we definitely chose things that were a little bit more certain to work. Maybe you can say some of the things that we tried.
So I think there's just, so you would want to pick up an array of different objects that are very different. And I think, like, we have some hardware limitations here. Basically, like, his grippers is preset at like some distance, so you could, like, it can only come in with an extender. And then if it's set at the very wide settings, then it cannot close fully. So there is like a natural limitation here, at least to NIRO, to what he can pick up. He does also have other grippers that we never really got to play with too much.
Sticky grippers or 3-finger grippers.
Yeah.
There's a
But essentially, I think the point is that it's hard to have too many different objects because you would have to make some decisions ahead of time.
I think one more problem would be certainly the calibration, because you have a hard object, it's easy to know when there is enough pressure to stop when you grasp it. But if you actually want to grasp a cat, which is a soft object, it's kind of hard to know, well, when do you stop? You should also know probably, how is the cat arranged in the 3D space? That's also probably a good idea.
Fix it. Yes.
Yeah, so very nice project. I mean, I was interested to see your kind of conclusions or the kind of ideas of what you would work on next. I guess you said state machine, object recognition, user awareness, and those mainly sound like, let's say, AI perception type of things. I mean, how do you assess? I guess is the hardware platform that you've been using sort of good enough for that? I mean, do you think that with the right perception and AI, you really could do a wide range of household tasks with that hardware?
Yeah, navigation is something that we spent quite a lot of time on, and we're quite limited in what we could do because we only use one input for navigation, and that's the library. So, two things that we thought could really improve the versatility of this robot is using an IMU, which is really like a JavaScript, which essentially can detect orientation in 3D space. So that is another way of ensuring that the alignment is indeed what the LiDAR indicates it is, and feedback from the wheels. So at the moment, we send instructions to the wheels, and the only way we know that those instructions have been received is if the LiDAR detects that the environment is moving around the robot. So that kind of feedback would allow more versatile orientation and localization and open up the opportunity for us to potentially enable global localization. So at the moment, we use local mapping, which enables us to move within a fixed environment at very specific points within that space. But if we use the SLAM-based approach and more sensors, it could really navigate in a brand new environment and build a map as it goes along.
This is, of course, something you're an expert in. But yeah, so I mean, for us, if you gave this to a customer today, they would have to pull out measuring tape, right, and start figuring out how their own home is arrayed and make sure that things are movable, which is why we think that's a really great area for improvement.
We're pretty happy with the state machine. We built it in a way that's quite light, modular, so people can take up components and shuffle them around and also extend them. So I don't think we would need extra hardware to do
A stronger battery can make a huge difference.
Oh yes, it's heavy, 200 kilos to carry on this little wheelchair base, so yeah, that's it.
Time for one more quick question.
You mentioned that when it goes towards the coffee and it locates it, I presume it understands the coordinates, then if you move it, it immediately recognizes that. What is behind that? Is there some...
We could even just show like a 30-second clip of
Can we
that.
answer that with a 30-second video? Maybe some commentary.
Yeah, go on. That's fine. Perfect. This is a good question. The question you asked, because we're proud of this. At first, he just kind of goes. He tries, and if he doesn't find something, he goes back down. But now he knows, based on this pressure and how closed his fingers are, whether or not he's received something. Based on that little input, we try again. So you'll see. That's that intermediate position that Kim was telling you about.
So what's going on now? It recognizes that the goal hasn't been satisfied.
Yes.
Yeah.
So he's basically checking his script if there's the force that he expected, and if not, he's reaching for it. And you can continue this way.
And this time he'll try intelligently with the other hand, like this. But yeah, he will. He'll switch between hands. You can show this to you later too. You come over to the other
Well,
side.
this is nothing rule-based. It's just saying.
It's procedural. For now, but these are things that you could optimize.
Okay, well, thank you.
Thank you.